Team Robot's goal this semester was to create an autonomous vehicle that can detect and avoid obstacles in real time. Our motivation was to create a more efficient and overall faster maze running project by using image processing instead of vehicle-mounted sensors like most projects you find online. We had a $400 budget to complete the project, and we chose to create a system with a Raspberry Pi as the heart of the system. Our project will detect the starting point, end point, and any obstacles on the field, and then it'll send a path to the vehicle, and we'll monitor the vehicle to make sure it's following the path to the goal. The communication between the subsystems will be wireless, and the vehicle will be battery powered to allow complete freedom of movement. We are detecting our obstacles with a PlayStation PSI webcam, which is set up on a stand above our playing field, and it gives us the image you can see here. Once the image processing system has decided on the best path around the obstacles to the goal, it will send instructions to the vehicle with a 2.4 GHz radio transmitter. The vehicle's battery is a USB power bank, which has a built-in 5-volt regulator and can provide up to 2.4 amps of current. This amount of power is necessary to run the 12-volt DC motors that are the main drivers of the robot, and the built-in regulator ensures that the robot's movement does not begin to slow down as the batteries discharge. The drive wheels are in the back, and the robot's balanced in the front with a roller ball bearing. This allows a lot lower friction when it's moving and turning. And the battery is being boosted to 8.5 volts by an XL 6009 boost converter. This is to provide better starting performance of the motors, and those are driven by an L298 motor driver for easier control and software with our Arduino Uno that's on board the vehicle as well. The L298 allows for speed control of the motors, and we're implementing a differential steering system. So if the robot needs to go straight, both motors are given the same voltage. If the robot needs to turn left, it receives a degree to turn, and based on the degree, the speed of the left motor is decreased in order to make the right motor run faster so that the vehicle will turn left. This allows a more continuous form of steering than a time delay based system that tells the robot to move a certain direction for a certain amount of time. And it also allows us to correct the direction in real time instead of having to wait for the robot's movement to stop and then correct.
This is a screenshot of the software running. Black represents obstacles, red represents vehicles, and blue represents targets. You can clearly see in the upper right corner how our image processing system captures the positions of different objects and displays the position of the center point coordinates. In the lower left corner, our console also outputs the results calculated by the root calculation system. However, our first generation algorithm has some shortcomings. The actual pixel size of the set needs to be hard-coded. There is no guarantee that you will get the best route every time. And if there are many obstacles in a row in the same direction, it may be impossible to calculate the correct path. Therefore, we decided to use a more mature A-star algorithm to calculate the path. For the A-star algorithm, we found some problems when using it. That is, there was too much noise during image processing, so we made some optimizations to the image processing system, just like the code shown in the figure below. We first convert the RGB image into an HSV image. Then the image is eroded and binarized. Finally, the black and white inversion of the results can eliminate most of the smaller noise and get a clear image.
The first feature of our software solution was using the A-star search algorithm. Basically, A-star allows you to find the quickest path from one node to another, but does not require an exhaustive search. As you can see in this demonstration, A-star prioritizes nodes with a lower F-score, which combines the distance from the starting node and the distance from the goal node. In this way, A-star is able to find the shortest path to the goal without exploring every possible path. To improve performance, we split the image into tiles with an adjustable size. Each node was the pixel at the center of each tile. A node was valid if no obstacle appeared in the surrounding tile. In order to ensure that the robot did not run too close to the obstacles, we dilated the obstacles according to an adjustable variable as well. The combination of these two variable definitions allow for greater user control when adjusting to a smaller or bigger maze. Finally, a huge issue with A-star is that you need to prioritize the minimum F-score value available, which means a lot of searches through the node array. To speed this up, we utilized a min heap so that we could find the minimum F-score value at 0.1 time. Once the path was found, we needed an efficient way to track the robot through the maze. At first, we tried to run A-star on every frame. This slowed down the algorithm way too much, and we were sending delayed information to the robot. The next solution was to run A-star in the beginning and merely monitor the robot through the video camera. This worked much better, but our original idea of using steps to get from node to node did not allow for any error detection. In the end, we decided to use two different sizes of red circles to track the robot. The front of the robot was always the smaller circle, so we were able to tell the direction that the robot was facing. By comparing the angle between the centroids of the red objects and the angle between the centroid of the larger circle and the next node in the array, we were able to calculate the direction the robot needed to travel. All that remained was to find a way to send this information to the robot in a useful format. The solution was to send the angle as an integer on the scale 0 to 180, with 90 being straightforward. If 270 was sent, that meant that the difference angle had surpassed a 90-degree turn, and the robot should travel directly backwards until able to make the turn. This worked extremely well, but required even faster read times from the webcam. This was solved by creating a multi-threaded program in which one thread read the frames from the webcam into a queue. The main thread merely fetched the next frame from the queue and tracked the robot's position and direction angle. This sped up the code immensely.
The A-star algorithm guarantees the shortest path, and we have optimized our dilation and tile size in the code to avoid clipping our obstacles or steering off of the playing field. The biggest strength of our project is the concise image processing code that allows for real-time speed, and the vehicle can move freely because of the differential steering system, which allows for better error detection as well. The biggest weakness of this project is the wireless transmitters, which save all transmission in a first-in, first-out queue that has to be flushed in order to follow our path properly.